coming back to our applet here, what we're trying to do now is take the idea of linear combination, whereby we had a couple of vectors, 4, 1 in this case, and -1, 2. And then we were taking some linear combination of the two. And just for now, I'm going to call those linear combination coefficients x and y yet again, to connect it with our original system of equations that used x and y as the variables. And then the question was, how do we find an x and a y? In other words, how do we find an appropriate linear combination that turns 4, 1 and -1, 2 into our right-hand side target vector 10, 7? And this was the linear combination formalism for a system of equations. And before we talked about your reading responses, we mentioned how what the entire purpose, initially at least, the computational purpose of using a matrix, is that it allows us to think of this linear combination, which really looks like there's a bunch of stuff happening, right? I've got a scalar multiplication happening here, a scalar multiplication happening there, and I've got an addition happening here, so that's a lot of operations all at once. But the matrix formalism allows us to think of it as a single operation on a matrix having these coefficients, so 4, 1 and -1, 2, operating on a vector, which we're going to write as a column, and the entries of that vector are the coefficients of our linear combination, x and y. And this, actually, there's nothing more to this than a definition. This is not deep mathematics. This is just saying how we understand the operation of a matrix on a vector. The vector that we're multiplying the matrix by just tells us which linear combination of the columns of the matrix we would like to take. So if I call this matrix A, as we are wont to do, and I call this vector x with a vector symbol on top of it, then to multiply A times x means take the linear combinations, take a linear combination of the columns of A. And the particular linear combination that we're taking is the linear combination whose coefficients are the entries of the vector x. So to get us some additional practice with that idea, let me clear out a little more space here. I'm making Moodle go away, which some of my faculty colleagues would love to be able to do just by writing with a pen. But let's suppose, just for the sake of example, that I've got the matrix, 1, 2, 1, 0, 1, 1, 1, 0, 1. So here's a 3 by 3 matrix. And I'm going to multiply it by the vector 4, 6. What do I do? So according to the upper left-hand corner, what I'm supposed to do is I'm supposed to take a linear combination of the columns of this matrix. And the coefficients of that linear combination would be 4 and 6, right? The entries of this vector. So in other words, this is asking me to take this linear combination of these 3 columns. Zach's shaking his head. Right. So this is the first thing to observe about matrix multiplication, is that it's not a free-for-all. Right? We cannot, in fact, compute this matrix product by this vector, because this would be asking us to take a linear combination of these 3 columns, but we only have 2 coefficients for our linear combination. So this matrix product is actually undefined. We can't do it. So what is the general statement here? How do I know when it's okay to multiply a matrix by a vector? What has to be true in order to succeed in multiplying A times X.
Has to have the same number of coefficients as it does columns.
Exactly. AX must have as many columns in A, columns of A, has to be the same thing as the number of coefficients. In other words, the length of my vector. No, I'm not going to say length. Let's say the number of entries in my vector. And because our vectors are arranged in a column themselves, we could think of the number of entries as being the same thing as the number of rows in that vector. So let's take that tack as well. So the number of columns in the matrix A has to be the same thing as the number of rows in our column vector X. And this is a requirement that otherwise this matrix product is completely nonsensical. We can't do it. So that's the first thing to observe here, is that we can't always multiply any matrix by any vector. The dimensions have to match up, okay, or else it's a no-go. All right, so let's fix that. So let me go back to this purported product that we were looking at before. And let's make it make sense by giving our vector 3 entries instead of 2. 4, 6, -1. So now I have 3 columns in my matrix and I have 3 coefficients in my vector to multiply by. So now we should be okay. So now that this product is actually well defined, how do we find it? How do we compute it? So there are a couple ways to look at this, but give me one of them.
You take 4 and multiply it by the first column.
4 multiplied by the first column. Great. 1, 0, 1. So let's keep score down here. 4 times 1, 0, 1. How do you multiply a matrix by a scalar? Sorry, a vector by a scalar?
So it would be 4, 0, 4.
Exactly. Distribute. So it does become 4, 0, 4. We know geometrically that that just looks like stretching the vector out. Right? That was the point of the applet yesterday. But from an arithmetic standpoint, we just distribute that scalar into our vector. So we get 4, 0, 4. So far, so good. Then what?
Do the same thing for the rest of them.
The same thing for the rest. So the second entry in my vector is 6, and that will scalar multiply the second column, 2, 1, 0. And that will give me, if I'm keeping score down here, 12, 6, 0. And then -1 multiplied by the third column, 1, 1, 1. -1, -1, -1. And now that I've multiplied all of those columns by the appropriate coefficients, what do we do?
You add them all together.
Add them all together.
All add the rows together.
Yes. Yep. And when you add these vectors, these column vectors, we add across the rows, as Catherine says. So 4 plus 12 minus 1 is 15. 0 plus 6 minus 1, and 4 plus 0 minus 1. Great. So multiplying a matrix by a vector, we're just taking a linear combination of the columns. By the way, I believe when people see matrices for the first time, anyone remember where they saw matrices for the first time? Was it in this class, or was it in
High school.
high school? Yeah, so when you see matrices in high school, is this the way that you usually learn how to multiply matrices?
No.
Yeah, I didn't think so. What's usually the way that they train you to multiply matrices in high school?
Did it like junior year, I forget. 4 years ago.
Multiply inside the
Yeah.
first matrix, you get the numbers. I don't remember how.
Yeah. So it ends up being equivalent, of course. But what they do, so what we did is we did all the scalar multiples of the vectors first, and then did all the addition at the end. But the algorithm that you usually learn in high school does them kind of simultaneously. What it does is it takes the first row of this matrix and this column over here, and it takes the products individually. So this 1 multiplied by this 4, 1 times 4, and then the 2 multiplied by the 6, and the 1 multiplied by the 1, negative 1 rather, 1 times negative 1, and then adds them all together. And that gives you the first entry of your resulting product. So, in other words, they completely sort of, when you learn matrix multiplication the first time, it's scrubbed of all of its vector reality, right? I should coin that word, vector reality. So you go across the row and down the column, and you compute what would be called a dot product of the row of the matrix with the column of the vector that's to the right. And that gives me the first entry. Then to get the second entry, we do it with the second row of the matrix instead of the first row. To get the third entry, we do it with the third row. And that's all well and good because it trains you how to multiply not only a matrix by a vector, but you can also use that same technique to multiply a matrix by another matrix. But when we're thinking of linear algebra from the ground up, as we are this semester, I kind of like the linear combination technique because it keeps the focus on exactly why we're doing this. Because linear combinations, after all, are how we were thinking of what it means to solve a linear system of equations in this picture. Right? That we're just trying to find the right linear combination of our two vectors, which become the columns of our matrix, but our two vectors that give us the right-hand side of this equation. And we're going to need that linear combination formalism to then later figure out what it means to multiply a matrix by another matrix. Why in the world would we multiply a matrix by another matrix? That's unclear at this point. Whereas it was a neat little trick that you can learn to do in high school, algebra 2 or whatever. But when we see matrix multiplication by other matrices, we'll, I think, have a better understanding of what exactly is happening there. So any questions on the matrix multiplication side of the house yet? It's a pretty straightforward skill, as you say in your reading responses, that it's a lot easier to wrap your head around than row operations are. Or at least the row operations themselves are easy, but the strategy for figuring out how to use them and in what order, that's the hard part. So what matrix formalism does for us now is it allows us to take that same linear system of equations that we've been looking at, which we express as a vector equation on the right-hand side, and if we forget for the moment that this matrix product really is just a linear combination, we take out this middle step here, and really, our linear system of equations has the following new form. Right? That we just have now a matrix A times the vector x equals this vector on the right-hand side. Let's call it B. That's the traditional name for the right-hand side vector, for whatever reason. So in the new formalism, the linear system of equations that we're considering takes the form A times x equals B, where x is my unknown vector that I'm trying to solve for. And so then every linear algebra problem now becomes solve for x, the vector x, in the matrix equation A times x equals B. And I'm going to put an extra bold box around that equation, because there are really kind of two equations that make linear algebra. And this is the first one, and it's probably the most important. AX equals B, because it looks so innocent in this format. If A were just a number, and x were just another number, and b were just another number, how would we solve this equation? If there were no vector hats and we forgot that these were matrices and vectors, what would it mean to solve AX equals B? It'd be a one-step equation. If x were a number, a were a number, b were a number, all we would have to do is divide by a. Because then x would be by itself, and the right-hand side would be our solution. Right? X equals b divided by a. But of course, linear algebra would be way too easy if that's all there were to this equation, right? Let's just divide by the matrix A and we find out what x is. Well, inasmuch as it's simple enough to describe what matrix multiplication is, describing what matrix division is a much more interesting question. And it's going to take us probably all of next week to come to grips with what it would really mean to divide by a matrix. when is it even possible? Because after all, matrix multiplication is only possible in a certain set of circumstances. Matrix division is possible in an even smaller set of circumstances. So the big question of next week is, when can we divide by a matrix? What has to be true about that matrix? And they're going to have a whole list of properties, all of which are equivalent, but all of which must be true in order that we can divide by a matrix and find a solution of ax equals b by just moving the a to the other side. So that's the theme of next week as we get into that.